All right, I think we have a good attendance. So let's get this started. Welcome everyone to the educational webinar. Thank you guys for joining. Today's topic is Siemens optimization solutions, where we show you the variety of optimization tools inside the Siemens portfolio. My name is Mason. I am the business development engineer from ATA Engineering. I am based off in our San Diego office. I'm very excited to be joined by John and May from Siemens today for the topic. Before we dive into the actual content, just some housekeeping notes. All attendees will be muted throughout the webinar. If you have any questions, you can type them in the Q&A chat, and we'll answer them real time, or uh, we'll unmute you at the end, and we'll have the presenter answer them directly. The webinar will be recorded and will be available on our ATA website and on our YouTube channel later on. And before I hand it to John and May, just want to spend a few minutes going over ATA Engineering, about who we are and how we might be able to support your team. So most people recognize ATA as a engineering service company. That's about 80% of our business. And we'll talk about the remaining 20% in a little bit. Our core founders have been together for over 40 years and have been having in the industry, have vast experience providing high value engineering services, focusing on test and analysis driven design. And majority of our business are in aerospace and defense industry. That's about like 70% of our business. But we also work on other industries like industrial mining, spacecraft, thing entertainment, and you name it. About who we are, ATA is an employee-owned business with a full-time staff around 200 people. Most of them have advanced engineering degree, as you can see on the right. Over 70% have master or PhD. We have 9 regional offices across the US, and as I mentioned before, years experience focusing on design, analysis, and test, providing high-value engineering services and at a really great quality. This includes everything from, structure design, dynamics, thermal, acoustic, CFD, and more. Test-wise, we are the leading independent modal test group in the US. They have lots of experience flying our team to the article location and do GBT and use that information to help drive the model. So that's about 80% of what ATA service business does. Aside from that, most of you joining the webinar today know about ATA Engineering. We are a Siemens VAR, value-added reseller. We not only sell the product, but we also provide software support and training materials to our customers. We really focus on products and solutions that we use internally, primarily design, analysis, and tests. For example, you see Simcenter 3D, FEMAP, Nastran for FEA, STAR, CCM Plus for CFD, HEATS for optimization, AIMSYM for 1D system simulation, and so on. And for test, we are one of the Siemens partner in the US that can provide Siemens testing hardware and software support. And just very recently, we are awarded the Partner of the Year in North America by Siemens, again, showing our dedication to support our customers. I think what sets ATA apart from other Siemens reseller is that we sell what we use, so our customer appreciate the familiarity of the tools. And it shows in our hotline support. Every time when you call our support hotline, you are actually speaking with an actual ATA project engineer who use the software every day and understand the problem. In addition, we teach a variety of classes, primarily dealing with simulation. We generate all the Siemens training material for the Nastran software. So a lot of time, if you want to go up online to Siemens and find a Nastran class, you ended up finding it in Denver or San Diego, because that's the 2 locations that ATA hosts the class and Siemens just taking the registration. All right, gotta keep this short because we have lots of material. Last slide before I hand it to May and John, just want to encourage people to visit the ATA website. We recently redesigned our website, so it looks really clean and different. You can find all the information on there, including hotline support information. This is one of the unique advantage getting your Siemens software from ATA. and free resources, including, past webinars, FEMAP APIs, white papers that you can download freely. All right. With that being said, I'm very happy and excited to introduce today's speaker, John Leahey and May Taylor. Both have over 30 years of experience in the industry and will show us all the optimization solutions tools inside the Siemens portfolio. Take it away, John, or May.
Okay, thanks, Mason. Let me just go ahead and steal the sharing and make sure I share the right screen. Okay, so you should be seeing my screen and hopefully the title slide. Do you
Yes,
see it?
I can see it. Awesome.
Yeah, okay. Thank you very much, Mason. Yeah, so my name is John Leahey, and May and I will be giving you guys an overview of NX and Simcenter's optimization tools out there. So this slide just kind of gives you a quick picture of what we're going to cover. As Mason highlighted, we definitely have a lot of information we would like to try and cover today. So probably the key, we'll start with what we call an implicit optimization, which is more of a blank sheet, and you're looking for the tools to help you to figure out the best way forward on your design. Or as well, we'll also cover explicit, which is you might have a parameterized model that you want to try and optimally size for different conditions that you're looking at. And then we'll wrap up by talking about some of the license options that you have. So obviously, since there's so many different solutions here, you could individually purchase those solutions, but probably the easier way to go is to leverage what we call the value-based tokens or value-based licenses, which allow you like, hey, I can grab any tool I need it when I need it, and we'll give you that highlight as well. Yeah, one thing just to kind of cover, because optimization is a very large topic, we're really going to be focusing in primarily and more on the 3D optimization tools. So looking at some of the capabilities in NX, and then likewise Simcenter. And what we could cover for a much bigger day would be a whole bunch of other different solutions for optimization. So things like model-based systems engineering, there's a bunch of different solutions within the Siemens portfolio. Likewise, 1D optimization or reduced order model optimization. Siemens recently acquired Altair, which has a whole other suite of optimization tools, manufacturing-based optimization. Of course, there's even greater detail in artificial intelligence, although May will touch base a little bit on that today. So to get started, we'll hand it over to May to talk a little bit about this implicit idea of optimization.
All right, thanks, John. As shown here, we have both NX and Simcenter 3D optimization solutions. Obviously, the goal is to streamline and automate your product performance process by searching the entire design space, finding the right combination of parameters that will yield optimal design and performance. And basically, this accomplishes two things. You can reduce design risk, accelerate innovation, and shorten time to market. Now, as shown here, you see we have two solutions for two different users, designers and analysts. Designers typically more familiar with NX CAD, solid modeling, assemblies, but yet still have a basic CAE understanding. Whereas the analyst, it's really you've spent most of your time in Simcenter 3D, you're familiar with the workflows, you have extensive knowledge of CAE, and some experience with optimization. So we kind of try to cover both areas or both personas of the people utilizing our software. So next slide, John. Go for it.
Okay. So what I'll talk a little bit about is to give a picture on the topology optimizer within NX, and then I'll hand it over to May, and she'll give you a picture of what that functionality looks like on the Simcenter 3D or FEMAP side. And one thing to highlight is you'll see embedded throughout the slides, we have a couple of different QR codes. And basically, those will just be little demo snippets. So we'll show you some demo workflows, but also wanted to give you some additional links to other demos or longer versions of that if you wanted to take a look at that following the presentation. But within the NX world, this slide kind of gives you a really good picture in terms of the capabilities from a general perspective with respect to generative engineering. So it's highlighted here. There's a whole lot of different functionality. You can kind of see this is resting on 4 key areas. One is, of course, dealing with the integration between CAD and CAE on the materials side. Second would be a very productive modeling environment. That's one of the things I really love about Simcenter 3D is it rests on a really sophisticated CAD tool and makes your CAE efforts a lot easier. Of course, what we're focusing in more on today is the multidisciplinary and multi-objective design space exploration and optimization. And then finally, there's some automation that's built into machine learning and things like that. Now, to kind of give you a large amount of different capabilities, you can see a lot of different areas within the NX world that cover generative engineering and then also capabilities that help you with additive manufacturing. But really, what we're trying to focus in on is just some of the things that we're highlighting here, and this one is going to be the Topology Optimizer. So the Topology Optimizer, the way I generally think about topology optimization generally is you can really think about it in 2 ways. One is this great tool to help you in the early conceptual stage where you have a clean sheet design and you don't really know exactly where you need to go. So maybe you know how you're going to hold or fix your part. You might know how it's going to be loaded and some material properties, but you're not really sure how to fill in this structure. And the second version would be, as highlighted here as well, is if you plan to do additive manufacturing, then it could also come up with concepts that would support your overall additive manufacturing process. So what you can kind of see here in this workflow, it just gives you a great picture of the overall process. When you first start with designing it or designating your design space, putting in any details for construction bodies, you go through sort of the normal process of adding what your design objective and constraints, any kind of manufacturing related constraints. Then you go through the normal loads and boundary conditions. You go ahead and optimize it, and then you get your result. So we'll show you this in a video format and a simple example. And again, there's tons of other examples out there that you'd be able to take a look at. So the nice thing about the Topology Optimizer is it has a very easy to use workflow. So because it is targeting an NX person who's spends most of their time in NX and they may be more of a part-time user on analysis type functionality, it has a nice workflow that just sort of guides you through the process of what do you need to set up and where do you go to the next step. So here you're just kind of seeing some of the options for setting up material properties. And just like anything else, you can either assign materials out of a library or inherit it from whatever you had already set up. Here we're going to set up information specific to what kind of constraints we have from a manufacturing assumption. So in this case, this might be where you have some bearing loads on your structure, and there's different options that you can consider. The kind of cool thing here is that, maybe on this structure, from a hand calculation, you figured out, okay, I know how thick this component needs to be to handle the bearing loads, so I don't need the optimizer to go crank away on that. But what you can then do instead is say, I've got that fixed, I can kind of size that as needed, and then I want to have the optimizer go ahead and work on what is the structure actually going to look like between those bearing load interfaces. So in here, we're putting in sort of traditional optimization type targets. So maybe my key goal here is to minimize the mass of the structure. And then we can put in some additional constraints for the system as well. So we put in, okay, we're going to fix the component in one direction. As we said, it's a bearing structure. And then we'll go ahead and put in a couple of different loading options. So you can see, we'll just go ahead and have equal and opposite forces. So we will essentially are going to have this designed partly for a lateral loading scenario. And then one of the cool things about Topology Optimizer is this ability to do your load case management. So you can have a lot of different scenarios and very quickly say, well, I want to have a scenario where I run just one load or another load, or maybe want to combine the loads into its own scenario. So you really have a lot of different capabilities that you can consider as you're setting up the model. Another nice thing about Topology Optimizer, it's actually really straightforward from how it's discretized or meshed. And so that was just showing you that step. And then, of course, this is showing you the result of getting the optimized structure out of the model. So what's really nice here is that this model, then you just can bring it directly back into NX and continue the process of designing with it. You essentially have this mixture of a convergent body and a normal body that you might be familiar with in the NX world. And then it becomes a feature like anything else, so you can suppress it. You can redefine it, based on other constraints or whatever that you need to. So this just kind of gives you a picture. We can kind of move on in the interest of time, but we were able to get some pretty good results out of this model. So with that, I'll hand it over to May for the Nastran version.
All right, thanks, John. Next slide. Okay, I'm just going to go through the process of setting up a Simcenter Nastran topology optimization. So this type of optimization actually leverages the finite element analysis process, and it'll actually remove elements from the model which are not needed for given performance targets. By doing this, it enables radical changes not possible with other forms of optimization. The resulting models are often organic looking, ideal for additive manufacturing. So within a single topology optimization, the user can have any mix of analysis subcases selected from linear statics, normal modes, buckling analysis, direct and modal frequency. And there can be different loads and constraints for each subcase. And there are also a large number of NX Nastran loads and constraints that are supported. So next, John. So there's a single design objective per solution, and this could be such things as minimizing the weight, minimizing volume, or minimizing compliance. Because in mechanics, compliance roughly stands for the inverse of stiffness. So to improve the structural integrity, you may often want to minimize the strains in the structure, which means minimizing the compliance or maximizing the stiffness. Or the design objective can involve frequency response, eigenvalues, buckling, or several others. You can pick your design areas. In other words, you can select certain elements of the model that the optimizer can operate on, leaving the rest of the model frozen. So only the elements you select will be optimized. And you can also pick design constraints, such as weight limits, displacement limits, or frequency limits for a particular mode. Next. And then finally, you can pick your manufacturing constraints, which are used to actually guide the design shapes with a manufacturing process in mind. Examples are shown here. They can include things such as planar symmetry, rotational symmetry, max or min member size, which is really the cross-sectional thickness of the optimized region. So there's a lot of capability there. Next. So once you set up all of this, you run the optimization. One of the results will be the material density results. And basically, at the beginning of the run, all elements are going to be normalized with a normalized material density of 1. Then as the solution progresses, it will remove material down to 0, which is complete removal for some areas of the model. And you can view this varying density at the end of the solution run, and then you can make and pick your desired selection, what material density you want. And shown here, it's shown at greater than 0.8. Next.
Reducing mass and weight of the components in your product can produce major benefits such as improved efficiency and reduced material costs. But figuring out how to reduce mass without compromising structural integrity can be a real challenge. Topology optimization can help you find the best lightweight shape for your parts that will still meet your performance requirements. This demonstration will show how you can use Simcenter 3D with NX Nastran topology optimization to get the best shape for a new airplane seat bracket design. Topology optimization is a finite element based approach, and we first begin with a mesh for the entire design space where the part could live. So the end bracket we want to design could fit anywhere within this green mesh. We also designate areas in the space where the bracket will connect to the seats, and we color those in red. For this seat bracket, we want to minimize mass with an upper limit of 2.5 kilograms. We also put fixed constraints on the bottom bracket connections where it will connect to the floor. NX Nastran topology optimization allows the analyst to dig deeper than what can be done with the designer-level topology optimization tool. For example, topology optimization in NX Nastran can support multiple solutions based on the same model to study the effects of different load cases and analysis types. In this case, we define two loads. One is a vertical load of a 99th percentile passenger in the seat during turbulence. The other is a horizontal load, like when a passenger in the row behind pulls on the chair to get up. After we define the design space and keep-out regions for the optimization run, we define a manufacturing constraint. Since this will be a die-cast part, we can define the pull direction, which means the optimization process will not create any internal cavities or undercuts that would make it impossible to remove the part from the mold. After defining the max number of iterations, we can solve the model. To view topology optimization results, we look at the density plot, and we can see the conceptual shape the solver was able to converge to based on the loading conditions. We can also animate through all of the iterations so you can see how the part took shape. Now, to turn this concept into a usable part, we can export this shape as a facet body. To do this, we select the density level that we want, 0.5 in this case, and then export. We can then go into the modeling module within Simcenter 3D and import the STL file we just created. We can also open the design space geometry and then use Simcenter 3D's geometry tools to trace the outline of the facet body and then cut the design space part until we have the desired shape we want. NX Nastran topology optimization helps CAE analysts use advanced capabilities to execute design concept studies and determine the best shape to meet your performance requirements. Visit Siemens PLM today to learn more about Simcenter 3D and NX Nastran.
Thanks. All right, so what I have next is a series of slides that kind of show the differences between the two optimizations and who would use it. So shown on the left is NX, shown on the right is Simcenter Nastran. So again, the NX version, simpler, single material, a certain set of loads that you can use and constraints, nothing too complicated. Whereas on the Nastran side, you'll get multiple materials, a lot of additional types of loads and constraints, manufacturing constraints. So there's just a lot more capability there on the Nastran side. Next. They use different solvers. Obviously, Nastran is using solution 200. NX mainly just structural linear statics. Nastran more capability, normal modes, buckling, direct frequency. Hundreds of responses are available for objective and constraints. Really, the NX side is really just a concept. Let's see if this works and try to optimize a better design up front. Next. Yeah, as I said, just fast early concept designs, whereas Simcenter Nastran might be used later on when you're finalizing your design and you want to make sure everything is the best that it can be, and obviously utilized for more advanced simulations. Next, John.
Okay, so we can jump over to what we would consider more of an explicit optimizer. So this might be where you have some kind of a structure that you've parameterized and you're trying to figure out the best way to configure the parameters to meet whatever your objectives are. So the first one we'll talk about is the NX Design Space Explorer. And as before, we have some QR codes if you wanted to kind of take a look at some of those videos and whatnot, that those are there for you. So kind of going back to our very large generative engineering slide for NX, you can see we're kind of focusing in on just one small area, which is the NX Design Space Explorer. And basically the NX Design Space Explorer is based on a much larger tool within Siemens that May's going to talk about in a little bit, which is called HEEDS. And so basically HEEDS uses a functionality that the analogy here is, let's say you're going to go climb Everest, but maybe you've walked at your local mall, but you haven't really done any kind of mountaineering. So you're going to end up hiring a Sherpa to kind of help you to navigate through all the difficulties. And that's a little bit about how the HEEDS actually work. So it's got a whole bunch of different strategies that are very sophisticated compared to kind of early optimization capabilities that's oftentimes would get stuck where like, oh, I've had a failed design, so I'm just going to kind of kill the optimization. Where this is very adaptive in terms of being able to handle all the different types of scenarios that it runs into. So from a conceptual point of view, this would be, you're trying to navigate your way up this mountain. And of course, there's a lot of different tools that you're going to need at different parts along the way to end up navigating that. So from an NX perspective, this is going to be more focused in on things that are going to be parameterized and measured on the NX world. So in this case, we would be looking at a simple center of gravity optimization. And then we'll talk about other examples for Simcenter 3D, and then May will also talk about even the more full-blown HEEDS capability. So as this simple example shows, you're just trying to go in and you have this small structure and you have the center of gravity right now for this object, and you want it to be aligned with the axis of rotation of this wheel. And so then it's a matter of like, okay, you could do the normal kind of modify and update and kind of see how things change. And of course, that's going to get kind of maddening after a bit. Whereas you can use this optimization capability to go through the normal process of like, okay, I'm going to tell the system what I'm allowed to change and then what kind of targets I want to have for the optimization itself. And again, in this case, you're just trying to minimize the distance between the center of gravity and the rotational axis. And then you're essentially leveraging a lot of the capabilities within NX, both on having various parameters that are driving the model and then various measures that come out of it in terms of whatever kind of metrics that you're generally interested in. So this is pretty open. There's a lot of capabilities. There's other little demo snippets that we have where, hey, maybe you wanted to optimize the shape of a milk jug or of a gas tank or something like that. So then you have some really pretty creative options for how this kind of capability might be used. So this is just going to go through. You can kind of see the actual optimization progressing in real time, and then to eventually end up at the optimum solution. So again, in interest of time, I can just sort of jump it right to where it gets to the optimum solution. And then, of course, what you have in this case is you'll be able to see how all of the various different iterations progressed. You can see what was feasible or not feasible. Did anything meet the goal? And then you can go ahead and update the model accordingly And of course, in this particular case, you can actually see that it met the objective that you're looking for. And then one thing to highlight, again, this is another QR code, but that one shows another example of Design Space Explorer with another tool that we're not even covering, which is the NX Performance Predictor, which is really kind of the underlying engine for the NX Topology Optimizer. So all the same kind of setup without the topology optimization piece, but that's another kind of good piece for you to take a look at. And then I'll turn it back over to May.
Okay, thanks, John. Next. Many people don't know this, but Simcenter 3D actually comes standard with geometric and sizing optimization capabilities. And this includes Simcenter 3D models as well as the associated CAD models. It provides classical capabilities for the selection of design variables and the objective and the constraint functions, together with optimization solution controls, as well as post-processing. So the process really is as shown here. You do a setup, you define the objective, your constraints, your design variables, and then you set your control parameters. Next. So your optimization can really include a mix of CAD and FE geometry. So you can include things such as the FE beam section properties, the shell thickness, the CAD model sketch dimensions, or CAD feature dimensions, as well as expressions. And then solvers that are supported include not just Simcenter Nastran, but Simcenter 3D Thermal, Flow, ESC, Electronic Systems Cooling, as well as MSC Nastran, ANSYS, and Abacus. So, and the types of responses for objective and constraints include things such as weight, volume, temperature, mass flow, joule data, etc. So responses can also include FE results, such as maximum displacement or average von Mises stress. So there's a lot there, and of course the solution data can be displayed in a spreadsheet, which is a lot easier to comprehend. Next.
Okay, thanks, May. So then moving on to the Design Space Explorer from a Simcenter 3D point of view, it's very similar to what we just covered on the NX piece, but it's going to have the capabilities of all the various model definitions that you have within Simcenter 3D, of course, as well as looking at the responses of the structure. So you can get in much greater detail, such as a simple component that you might be looking to reduce the weight. You can get into composite structures, really complicated structures like a rotor for aircraft or stationary power aspects, electromagnetics, acoustics, thermal. So there's really a whole host of different ways that you can use the Simcenter 3D Design Space Explorer. So really, again, sort of building on that Sherpa type of a functionality and the HEADS functionality, you can really think of both the NX and Simcenter 3D Design Space Explorer as grabbing a subset of HEADS, which May will talk about, and then giving you that capability to go ahead and really explore the design space with a lot of capabilities to find the most effective design for your particular case. So this is just a simple example of a singular component that you're looking at, and then all the different iterations that you can explore, and then you can see the baseline design and the improved design. And in the particular case of this example, you can see that they're able to get almost a 20% reduction in the mass of the structure while still maintaining all of the various constraints that were important for the structure, stiffness, modal frequencies, whatever were included in that particular model. And again, just as before, we have a nice little QR code if you wanted to jump into that functionality a little bit more. And then so with that, I'll turn it over to May.
All right, thanks, John. All right, finally, the Simcenter Nastran optimization. It really is a capability that enables customers to outline design sensitivity to performance conditions to yield optimized design. So optimization can be applied to here a broad range of Nastran basic analysis types, such as linear statics, normal modes, buckling. But in addition, it also includes a broader range of optimization capabilities associated with the advanced analysis types, such as superelements, dynamic response, modal frequency response, direct frequency, modal transient, acoustic, static aeroelasticity, and flutter. So you get a lot more capability. You can reach into a lot more different types of analysis that are more advanced. It does utilize efficient algorithms. You can use hundreds of design variables. However, there is a limited number of optimization algorithms available, and you would have to have some general understanding of what they are. And there's only sequential simulation execution. So there's advanced capabilities, but there are some limitations as well. Next. All right, this is the fun stuff, the HEEDS. Okay, HEEDS is a great product. I just have to say that. It automates and transforms design space exploration and optimization. So instead of starting with a specific design, utilizing simulation to understand how it performs, and then you do manual iterations to improve it. Now users can just start with their performance objectives. Start with that first. And many of our customers have said that HEEDS is game-changing technology. And the really great thing is that HEEDS can be used by any and all designers and engineers. There's no expert optimization knowledge that's required, and that's usually what have held customers back in the past. So next. So in this example, we're trying to optimize the overall design of a car for better traction and stability while also reducing drag. So it's a multi-objective analysis. Whereas traditional design would focus on a specific design configuration and suffer from a slow, arduous process, HEEDS sets a vision for transforming design with automated design automation. So in this example, utilizing HEEDS, there was actually an 8% reduction in drag and a much faster solution turnaround time, which is, in my opinion, pretty amazing. So next. So let's look at another example in a bit more detail. So let's suppose you were on the design team and you were going to design a cooling system for a desktop computer. Now today, and in many companies that we visit, it starts with the design department. They have an initial design, then they send it over the wall to the engineering department. They analyze the performance, they provide feedback, then they throw it back over the wall, and they analyze the design, and they make the changes based on the recommendations of the analysts. So you can probably agree there's too much going back and forth and too much emphasis on the initial design. It's slow, tedious, and repetitive. So the vision we want to set for you is using HEEDS, collaborative design process, and you truly start to understand the physics and the behavior of your products. So next. So here we're utilizing HEEDS to run multiple simulations. You're going to find the best compromise of trade-offs. We're changing the location of the fan and vents, as well as the size, shape, and configuration of the heat sinks to find designs that provide the lowest weight for a given design temperature. So, I mean, you can imagine trying to do this manually. It would be quite overwhelming for the people that were involved. So next. So after 200 variations have been explored, we discover a much better design, a full 51% reduction in mass, and it's accompanied by a 25% improvement in cooling. And this is modern design exploration utilizing HEEDS. So next. HEEDS, and the really cool thing, HEEDS works seamlessly with all simulation tools that are shown here, as well as any internal software programs. It can work with any physics, And with any of your simulation tools, whether they're commercial or internal legacy tools, they can be 1D, 2D, 3D, can be based on FEA, CFD, or any other methodology. So the bottom line is you don't need to change your simulation tools. You just need to connect them together effectively with HEADS. In other words, use HEADS to wrap around your current workflow that's utilizing your current tools. So next. So what is the actual HEADS process? So the process begins with a validated and robust CAD and CAE model that can be easily rebuilt with changes in design variables. Next, the user automates the process of simulating one full design workflow using a variety of CAD or CAE tools, and perhaps even a costing model included as well. This process flow can be as simple and complicated as necessary to fully simulate the behavior of one design or one virtual prototype. Next, once the workflow is automated, the user defines how each task in the process is simulated in a high-performance computing environment so that many variations can be quickly explored. Some tasks can be assigned to Windows computers, others to Linux clusters, still others external cloud resources, and all tied together by a central orchestrator, which is HEADS. Next. This step involves the use of modern direct search techniques to efficiently explore the full design space, quickly discover better designs in a minimal amount of time. And then finally, the user can examine sensitivity, robustness, and variable interactions of the best designs that enable them to gain insight in understanding how performance will be affected by any changes to the design. So you really start to understand which parameters have the greatest effect on your overall design performance. And this is state-of-the-art modern design exploration, and it's built into HEADS. So next. Okay, here's an example of HEADS as applied to automotive bumper design for crash safety. So supplier design, they wanted to automate the process of exploring bumper design. They wanted the lowest mass that satisfied all design and performance constraints. Now, in reality, their model contained over 60 variables and 9 mandated FEA crash load cases. However, just to prove that automated exploration would yield high return on their investment, they did a subset proof of concept, and they involved 20 design variables and 2 load cases. So HEADS automated the process involving NXCAD for 3D modeling, LS-DYNA for crash simulation, and Python for model execution and post-processing. Next. After 100 evaluations across 12 cores, HEADS discovered a design that reduced their overall bumper mass by 32% over the baseline design. Next, note that unlike that previous design exploration techniques, there's no need for HEADS to simplify the problem or reduce the number of design variables. In fact, with HEADS, the more variables you include, the better chance you have of truly finding an innovative solution. In this case, they did a 32% reduction in mass. So next. So at this point, you're probably thinking, yeah, that looks great. I've seen design exploration tools. What makes this so much different and so much better? So, well, you're right. Optimization tools in the past were lacking. I mean, they suffered really from 3 fundamental factors. The models weren't robust. They didn't rebuild easily or reliably. You had limited compute resources, and the search strategies were too inefficient and too non-practical. So we've changed all that. So we no longer ask the user to simplify the model. When they were asked to simplify it, then they were asked to choose the algorithms, and most analysts, this is not something they're familiar with. So it introduced too much error too much iteration, too much expertise was required from the simulation engineers. So as a result, it got relegated to expert users, and even then, the gains were usually very limited. So next, we've removed all the bottlenecks and barriers and created what we call a modern process. There's no need to simplify the model. There's no need to select algorithms. There's no need to use one search strategy. There's no need to tune the algorithms, no need for iteration, and no errors produced. Bottom line, there's no need for optimization expertise. It's built into HEEDS. So next. I just want to finish up with a fairly complex example just to show you the range and capability of HEEDS. I'm not going to go into too much detail, just the highlights. Here's an example of an industrial gas turbine company and how they can obtain a full picture of how some geometric features influence stress. I mean, as you see here, there is a lot of different elements involved. You have 4 different portals, NX, Simcenter 3D, Nastran, as well as a generic one. There are a series of different variables, geometric, as well as mesh density material. So there's a lot of complexity in this particular problem. But the point is that HEEDS can automate this entire complex problem and come out with an optimized design. Next. And they were able to really truly understand the design space and how different geometric features actually influence the stress distribution, which trying to do this manually would be really, really difficult. Next, and I just want to end with the HEEDS AI simulation predictor. This is a fairly something new. Because it addresses typical challenges of multidisciplinary optimization. Typically, the time is long, the cost is high. So we've introduced an AI predictor, and we've had some pretty successful examples on reducing the time as well as reducing the cost. And we can come back and revisit this if this is something that you're interested in. So next. Go ahead, John.
Hey, yeah, thanks, May. Yeah, so one thing we just wanted to highlight for everybody is how would you actually purchase these different capabilities? So certainly you could go, oh, I really know I need to have the NX Topology Optimizer or the Simcenter 3D Design Space Explorer. So I'm just going to buy that as a license. But probably a more cost-effective way is to leverage what we call value-based licensing. So we call these tokens. And essentially the tokens give you access to all sorts of different types of functionality. And then when the token is in use, then you're using that solution. And once you're completed using that solution, the token goes back into the pool, and then another user can check that out. So it's kind of like a library book type system. So you can see here with the Simcenter 3D tokens that it covers a whole bunch of different environments and solvers. And of course, it's also highlighted in the bold, but it also allows you to access a lot of the things that we talked about today. So the Design Space Explorer and Topology Optimizer and even the Performance Predictor, which we had talked about. So with that, I think we are finished. And if you guys have comments or questions for us, you can send an email, or I'll turn it back over to Mason if you'd like to wrap this up today.
Thanks, John. Thanks, May. We do have some questions. I see one over here. So I'm just going to read it out. What type of FEM elements does VMAP provide for NX explicit optimization, i.e. PComp, core thickness, or layups?
John, I mean,
can you repeat the question?
Yeah. What type of FEM elements does VMAP provide for NX explicit optimization, i.e. PComp, core thickness or layups?
So you're talking about composite design, I assume? That true?
I think so. Not sure.
I mean, we can, I don't know that off the top of my head, John. I don't know if you do. We can certainly find out.
Yeah, I'd probably try and find out. There is a really good example. There's a YouTube channel called the Simcenter 3D Tips and Tricks. And there's a whole example in there with composite optimization. So I can try and bring it up right now, or if you would want to share it with people afterward, that's probably one good place to look at for that particular question. But we can also dig into that. If you have the person's name, we can try and follow up with them.
Yeah, she just added it's a composite panel interface with VMAP.
Yeah, we can, you can look into that, John. We can
Okay.
and provide that video too.
Awesome. Thank you. I don't see any other questions so far. If you have any questions, just type them into the chat, or we can unmute you that you can answer them directly.
Yes, I just wanted to show everybody, there's a really great site that one of our colleagues puts up tons of models for different examples. So there's one specific in here for composite optimization. Yeah, so there's a whole bunch of different laminate composites. So there's even this laminate composite optimization example, which of course that's an ad. So
Yeah, I mean, I know the question was with
What is a
reference
model? I think you can ask a million.
with reference to VMAP, and we can certainly dig into that. But most everything that's can be optimized in Simcenter and is available in VMAP is there as well. But we'll verify that. I guess we need a YouTube channel on VMAP, John, as well.
All right. Don't see any other questions. Since if that's the case, so if you have any other additional questions that you don't want to ask here, feel free to reach out to ATA, to me, or John, or May. We'll be able to follow up with you. With that, I think we'll just end this a bit earlier, with giving you back 5 minutes. And thank you again, May and John, for the well presentation.